how I would do it. And you don't have to write this one down unless you want. If you've done the delta math and you got it, cool. This is just a little feedback for you on how I would approach a problem like this. Okay, so this level 4 is delta math during the types of problems are ones that involve two radicals. So I have two square roots. And one of the challenges is how do we get rid of the square root? Well, we always want to isolate, but right now the left side is not isolated and the right side is. And no matter what kind of work I do, I can't take this square root of 9x and combine it with the square root of 5x plus 11. So in that case, what we're going to do is we're going to jump right into getting rid of one of the radicals. And I know yesterday we wrote this square root here as a 1/2 power, and then we raised both sides to 2 over 1. We did that for a special reason so you guys get used to that notation. But to be honest, right here, just square both sides. When I square both sides, the right side, the square and square root reduce each other out, and I'm left with 5x plus 11. It's the left side that requires us to do a lot of work. So, this part right here, I'm going to do side work. And we have to think of what does it mean to square something first. Squaring does not mean just take everything in the parenthesis and square it. Squaring means multiplying it by itself. So if you write it out as a multiplier of the square root of 9x plus 1 times the square root of 9x plus 1, that tells us that we actually have to do a little bit of multiplication. And for this one, I like the area model because it helps me visualize things. So I have to multiply all those pieces together. And it's actually the first box that is kind of interesting. I'm going to multiply. So this is what I'm thinking in my brain. I've got the square root of 9x times the square root of 9x. Well, when I multiply something together, isn't that the same as squaring it? And then, doesn't a square and a square root reduce each other out? So this is what my brain is thinking in red to give me the 9x. Okay. And now I've got positive 1 times the square root of 9x. So that's just positive square root of 9x. Same thing in this box. And then 1 times 1 as well. Now, we do have like terms here. These two square roots of 9x, I have one of them here and one of them here, and they're going to add up to give me 2. So all that box will work out to be 9x plus 2 square roots of 9x plus 1. And I know this doesn't look like we made the problem easier or simpler right now, but look at what we did. By doing this first step, by squaring both sides, we got rid of one of the radicals. And what's left over now is just a single radical. So my goal right now is to take and isolate that square root of 9x. And I didn't draw that perfectly. That should go all the way over. So now we have to do any type of order of operations to move everything over and isolate. So I'm going to subtract 1 to both sides. And at the same time, I'm going to move the 9x over as well. And that way, the 1's go away, but the 9x goes away. And I'm left with 2 times the square root of 9x. So now now, I still have to isolate the square root of 9x. So this times by 2, I have to move it over with division. And notice how I divided all pieces by 2. The one way I think about these problems is every time I perform a new step, it's like starting over with a brand new problem. What do we have to do? We still have to isolate the square root of 9x. Well, now it's isolated. So now I have to undo the square root by squaring both sides. And again, we could have rewritten this as the 1/2 power, and we're raising it to the reciprocal. So that's really friendly because we get rid of the square root, so I have 9x. But of course, there's more work to do. Now I got to FOIL and think about what does it mean to square negative 2x plus 5. So I'm going over to my side work again, and I'm going to FOIL that. Now, if you can do these FOILs in your head, which eventually you probably will be able to, you don't have to show any of this work if you can do it in your head. So I think I'm going to just go ahead and do FOIL using the arrows. And then I do notice that once I FOIL that, the two middle terms are equal. So you can actually add those like terms to give me a negative 20x. Looks like a weird 0. Now we finally, after all that, we finally got to the spot where I don't have any radicals. And this problem now turns into anything we've learned in Chapter 4 or Chapter 5. So, my goal then is to move the 9x over to the other side. Again, you don't have to show those steps. You could just say, well, that's going to give me a negative 29x. And of course, this is not going to be a super friendly problem to solve. Now, you have two options. You can always do the quadratic formula when you get a trinomial equal to 0. That will work every time. But I have a feeling this one is factorable. So I go back over to my side work. And I'm going to try to factor that big trinomial. And we multiply the corners. 25 times 4 is 100 x squared. And then I'm thinking, well, what times what gives me 100? That's 29 units away from each other. Or add up to give me 29. 4x and 25. However, they both have to be negative. Now we can play the factor game vertically. Those boxes share a 4x. The other vertical pair share a negative 25. Horizontally, we have an x, and we have a minus 1. The best part about the box method is you can check to see that these boxes all work out and everything's multiplied together, so these are the correct factors. equals done. We're going to set each parenthesis equal to its own 0. It's called the zero product property. And then quick algebra to solve the first one. X equals 1. The second one, if I add 25, that would give me 4x. So why not add 25 and then divide by 4? So after all that, are we done? Oh, right? Of course there's more. What do we got to do? Check. We got to check to make sure that are these actual true solutions. So I'm going to do this quick. I'm just going to come way up here, steal this. If it'll let me, there we go. Just so I have something to make reference to. Now, there is something that sometimes, oh shoot, I erased the warm-up that had it. I'll show you after this. Anyways, so we could probably check the first one in our head. What if I plug 1 in here and here? Well, 9 times 1 is 9. The square root of 9 is 3. So 3 plus 1 is 4. Okay. And then here, 1 times 5 is 5, plus 11 is 16. Square root of 16 is 4. So I know 4 equals 4, x equals 1. That works. What about 25 fourths? You could grab a calculator here. I'm also going to show you another way to do this that is kind of cool, that helps us review properties of radicals. I don't expect you guys to do this the way I'm doing it right now. But here's a cool property. Every factor can be written under its own square root. For this specific case. Now what does that turn into? Well, that turns into 3 times 5 halves. And then 3 times 5 is 15, so that's 15 halves. And then just don't forget to add that plus 1. Well, instead of thinking of it as 1, I might call it 2 over 2. So I get the left side simplifying down to 17 halves. Or if you did your calculator, it would be 8.5. How does that work over here? Well, this one isn't as friendly. However, we've got 25 times 5, which is 125 fourths. And then if I changed 11 into 44 fourths, that will give me 169 fourths, which 169 under its own square root over 4. Well, the square root of 169 is 13. Square root of 4 is 2. And there, you can see it does not produce an accurate result. Therefore, we come up here and say that we found an extraneous solution. It doesn't get much more lengthy or challenging than that. I think this whole year, that's about as hard as a problem you're going to do. Okay, so don't get caught up in checking by hand. I hope you just grab your calculator and check. But hopefully that gave you a little bit of feedback on how do we approach it when we have more than one radical. Okay. All right, so we're going to jump into this, I don't want you to write this part here. We're going to actually introduce something called function notation, which you've seen before, but we haven't dealt with a lot. So we're really going to just review some basics here with this page. And so you don't have to write this part right here. It says combining functions with addition, subtraction, multiplication, and division work exactly the same way they do with polynomials. So the only difference is instead of just saying here's a polynomial and here's a polynomial, add them together, we use function notation. So what I'd like you guys to do is try these three problems. I want you to do g minus f of x, knowing what g is and what f of x is, and then do g times f of x, and then do g squared. The thing here is we can basically tell you to do operations without setting the problem up for you and just name it by function. So here we have subtraction. Remember, we don't like to think of it as subtraction. We like to think of it as adding the opposite. And then we can just combine our like terms with addition. So I have a negative 3x squared. I have a negative 2x. And then I have 1 plus 7, positive 7, to give me 8. And that's as far as we can go. Yep. Oh, shoot. Did I write it wrong? Okay. Thank you. Originally it was plus 7. So then when I change it to the opposite, yeah, it's negative 7. I wrote it wrong. And that'll change my constant term. So then I've got 1 plus negative 7. Okay. Good catch. The next one is just multiplying. Right? We're going to FOIL. Or you could use box method, whatever you want to do. But I got negative 3x squared times negative 2, so that's negative 6x to the third. Negative 3x squared plus 1 times positive 1. And then I'm going to bring the positive 7 over. And there are no like terms, so that's as far as we can go. And then the second one is really testing the idea of, do you understand what it means to square something? They want us to take g and square it. So we have to write the meaning of squared. We cannot just square each piece in there. Usually that's what a lot of kids try to do if they make an error. So then we're going to FOIL. We get a positive 4x squared. I'll get a negative 2x, another negative 2x, and a 1. And then my final answer. Now, unfortunately, we're not just doing that today. This was to set the stage that, you know what? We can identify functions by their names. F of x or g of x or maybe h of x, r of x. It really doesn't matter. But they have a name. So how does this tie in with what we're actually doing today? Well, let me set the stage a little bit. I do not want you to write this. We're going to go fairly quick through it. And this is just, remember we did f of 2 a while ago? I think it was to start this unit, maybe last unit. And we just said, well, if I tell you to find f of 2, don't you just plug 2 in for x and you simplify? The answer is yes. But watch how this works really quick. And again, don't write this. So let's think of f as a function. It's a machine. It's going to do the same thing every time there's an input. So if I have 2, 2 is my input, or x equals 2 is the input. That's going to go into the function f, and then something's going to happen. Well, what's going to happen is exactly what f is programmed to do. F is programmed to take that number, square it, times it by 3, and add 7. So 2 squared is 4, 4 times 3 is 12, 12 plus 7 gives me 19. Now, what is 19? 19 is the output. Nothing special there. But what if? Here's the new part. What if I tell you now to perform another operation in order? So what we're going to do now is we're going to take this output from the first piece, and what does it now become? Comes the input. It's going to go into the function as a new input. So I'm going to take 19 and plug it into G. But G has a different program. G tells me to take the input and times it by -2 and add 1. So G is -2 times something plus 1. Well, that something is the answer to the first piece. And then what comes out of that is the answer itself. So that's what? -38 plus 1 gives me -37. So what did we actually just find? We found the first answer was f of 2, but then we took that answer and we plugged it into G. Everybody see this notation? This isn't multiplying. It's an inside-outside function. That's called a composition, and that's where we're headed today. So, what I'd like you guys to do is just in your head, I want you to do this one. Oops. What if I have G of 3? What is the output going to be if 3 is my input? -5. Cool. -5 comes out. How do we get that? 3 times -2 plus 1 is -5. Now, there we go. What if I tell you to perform G again? What's your new output? What'd you get? 11. Yeah, 11, right? It's -2 plus 1. My new output is -5. That gives me a positive 10. Now I get 11. So what is this answer? Well, this answer is, what did I do first? I did G of, I already got G of 3. And then that answer was applied again to G. So, sometimes people like to think of the movie Shrek when we do these, because we have onions. What do onions have? They have layers, right? Composition of functions have layers. The only difference, we start with the innermost layer, and then we apply the outermost layer. So, if I told you right away, do G of 3, you would have to deal with the inside part first, the red part, plug 3 in and you get your answer. And then you take that answer and plug it back into G again, and that will give you your final answer. Now this could keep going, right? I could say, do G of 3, or G of 3, and you would just keep going and do another G. All right, so visually, how does this look like if we're giving a graph? This is one of the problems that you'll see on Delta Math tonight. It's the same idea of what we just did, but I want you to just notice how it's set up. So here's the graph of F, and here's the graph of G. They're going to tell us to find G of F of 4. So I want to think of this in terms of layers. I need to find the layer, the inner layer first. F of -4. It's kind of hard to tell, but what would you say F of -4 is? If you can see the graph back there. -0.2. Yeah, it's kind of tough. So like here's where -4 is. It's actually right on this line, and I think it's meant to be -1, but you're close, especially with a 4 graph like this. So this output is right there at -1. So now I know the inner layer has an output of -1. So now what am I going to do? I need to find G of -1. Well, now G is a different graph. What is G of -1? If I go over, oops, sorry, I took your answer. If I go over -1, where is the output? The output is right here at -3. So that answer is -3. Why don't you try this one in your head? You don't have to write it down. I know the graph isn't perfect. It's kind of hard to see. All right, let's take a look. So we got layers. Let's deal with the innermost layer first. So f of -9. If I go over -9, here's -9. I have to go up until we hit that point, which looks to be at 4. So then this answer, the inner layer answer is 4. And now it's telling me to find G of 4. So now I have to go over 4 on the graph of G. And that's going to get the output of 2. This one, we can't do this one. Unfortunately, it doesn't work by the way this graph is set up. So it has a special notation. But why don't you try this last one in your head? Do f of G of -5. What'd you get? 8? It's, again, if you had this graph in front of you, you would be doing it much faster. But now, look at the inner layer. It's changed. Now we have to go to the graph G, and I got to figure out where is G of -5. So if I go over -5, here's -5 in the x. What is its output? Its output is -7. So now I have to do f of -7. So I'll go over to the graph, -7. Here's -7. Its output is right there at 8. There was something in the chat that I missed, and I think it was on the last one. Somebody said they got 7. Let's see, on the second one, I got +7 instead of +1. Did I make another error? What? Where? Goodness. Yeah. 7 times 1 is 7. All right. Good catch. Glad we finally fixed that. Okay. So, what if we change our thinking? Because what I just showed you is called a composition of a function, and I was just plugging numbers in. But what if we don't plug a number in? What if we plug a letter, a variable in? Okay? So don't write this. This is setting the stage just to help formulate your thought. But what if I take x, and x goes into the function of f? What comes out? goes in, an equation has to come out. And it's going to program, we're going to take x and we're going to square it, times it by 3, and add 7. So what comes out is 3x squared plus 7. Now, this is the important thing to remember. X was my input. It went into the function. I have a new output, right? Which is the original equation. Nothing special there, but what if I apply that same concept to G? So what if I take this new output and it becomes my input? It's going to go into G, and it's going to do whatever G is programmed to do, which is take your input. Remember, x is like an input. It takes the input, it doubles it, a negative times by negative 2, and then it adds 1. So watch what happens. So G is going to come out, and we're going to take whatever that new input is, which is the entire expression for f, and it plugs it in. So it's like putting one function inside of another function, and now the only thing that's left over is we have some algebra. What if I distribute here? And then I can add my terms. And what did I just do? I took the function f, which was the innermost function, and I plugged it into G, and I didn't come up with a number, I came up with an equation. That's when we piece these functions together, it's called composition of a function. Once you do the algebra, you can't see where the original equation came from, but you know where it came from because of how the problem started. Why is that beneficial? Let me show you this really quick. Didn't we just take 2 and plug it into f? And then we plugged it into G, and we got negative 37. G of f of 2 is negative 37. That's kind of a lot of work to do, right? 2 different pieces. Wouldn't it be better to do it all in one step? Now, let's check really quick. What if I took and told you to find G of f of 2 now? Since you already have this equation, we can plug 2 in there. Well, 2 squared is 4. 4 times negative 6 is negative 24. Minus 13 is negative 37. The same answer we just got. It's just a more succinct process of getting it. So, here's what I want you guys to write down. This part right here is the big idea of the composition of a function. Now you'll notice there were some examples that we just skipped over, and they had this little circle. That's the word of. So when we read that, we would read it f of g of x. But instead of, and it's not the word fog, it's actually written this way. F of g of x. So I like to write it the second way, because then you can see the layers. You can see g is the innermost layer, and f is the outermost layer. So what we're going to do is we're going to take the function g as the input. That's going to go into f. We're going to use the same f and the same g we used all day. And we're going to evaluate these two expressions. Now, if you're somebody that likes to use different colors, this would be a perfect time to do it. If I see fog, right, we're thinking f of g of x, I like to think of it this way. F of g of x. G is my innermost function. Well, wait a minute. We know what g is. Wrong color. So instead of putting g, we're going to call this f of 2x minus 1. And remember, whatever's in between these parentheses here is my new input. So this entire red negative 2x plus 1 is the input that is going to go into the function f. So what is the function f? It's 3 times something squared plus 7. But that something is the equation negative 2x plus 1. And then we're not done here because now we have to simplify. And you might require some side work. If you can do this in your head, awesome. But we really got to think about the meaning of square. So we can FOIL that out. We can use the box method as side work. I did part of that in my head. If you don't like it, you definitely can do the side work, but you should get 4x squared minus 4x plus 1. And then we're still not done, right? Because that 3 is a multiplier. Then I have to distribute the 3 to all those pieces. And then my final step, add the 2 constant terms. So that's what happens when I do f of g of x. All right. I'd like you guys to try g of f of x. And if you need the extra way to write that, we would write that as g is on the outside, f is on the inside. So go ahead and give that a shot, see what you get. take a look. So now f is the inner layer. And we know exactly what f is. F is 3 times x squared plus x. So I'm going to replace g with what f is equal to. And then we know what g is. G is negative 2 times an input plus 1. But that input is not x, it's the new function f. And now it's not as much algebra. We just have to distribute the negative 2. We get negative 6x squared minus 14 plus 1. And we get negative 6x squared minus 13. It takes some getting used to. Once you do a handful of these problems, you start seeing the patterns and routines, and it becomes much better. Okay, so that's one thing. This is called, remember, this was called function composition. It's a function that's made up of 2 or more different functions. So we got one last concept to talk about here, and it's called inverses. It's not directly related to this. It's kind of a separate piece. We just had to throw it in, and today was the best day to throw it in. So if you're looking in your book, this is from section 6.4. Don't worry about writing this page. Okay? We're going to just do an example, and I'll give you all the notes for that example. So, but what is an inverse? You've heard of inverse operations before. Addition and subtraction. If I add 5 to something and then I subtract 5 to something, those undo each other. Those are inverse operations. One way to find inverses is to interchange the output and the input. So we flip them around to create a different relation. If you think of it, here's a question that an inverse basically asks. If I know the y value, what is the x value? Or another way to say it, if I know the output, what's the input? How did I get that output? That's what we're doing with inverses. So, this is an example from Delta Math. And I want you to write this one down, and we'll take formal notes on this example. The process is the same. It's just sometimes a lot of algebra. So they give us a function f of x. And there's a lot going on here. It's 3 times the cube root of x minus 1 plus 10. And then they say find f of negative 1. That's our new symbol. That little negative 1 up there, which doesn't show up greatly, it might be better. That means find the inverse. So what do we do? First thing we do is interchange the input and the output. Another way of saying that is we're going to switch x and y. And I'll show you how we do that. Step 2 is to solve for y. the last step is just to rename it. Because that's what they want us to find, is they want us to find this function called an inverse. So we just rename it as f of -1 or y of -1. All right, let's go through these steps. So what are we going to do? We're going to take the given equation, which, by the way, remember f of x, that's an output. That's the same thing as y. So when we say switch x and y, we're calling the f of x y. So my first step is to take the x and y and just rewrite them in their own positions. Right? So you can see I physically switched the location of x and y. Step 2 is do all the algebra now to solve for y. So we're going to get y by itself, which means we're going to follow backwards PEMDAS. Right, so the first thing I would do is this plus 10 has to move over to the other side with subtraction. So we're going to subtract 10. And then we have to deal with multiplying. So I got that times by 3 has to be brought over. And you have a couple options. You can divide by 3 if you want. You could get x minus 10 all divided by 3. You could times everything by 1/3. Or you could divide each piece by 3. There's a lot of different ways to write it. It might be best just to leave it like that. Well, that takes care of the parentheses. Now I have to add 1 over to the other side. So the minus 1, we add it over to the other side. Now what's my last step? We've got to get rid of the cube root, and the only way to do that is to raise both sides to the power of 3. So when I do that, you can see over here we get y left over, and then we're just going to rewrite and here's a hint. Leave it like this. Don't cube this out. Right? We don't want to completely ruin your life at algebra. So now notice, I solved for y. I have an equation that says y equals. However, this is not the function y, it's the inverse. So we just are going to rename it by putting a -1 there. And that's the last step, is rename it. I could have said f of -1 as well. Both of those are equivalent. So you could name it either way. But there is my inverse function. So we didn't do a ton of these examples, but the process is the same. Switch the x and the y. Use any algebra means to solve for y. And when you're done, you rename it with our new symbol for inverse. Okay. So we have a couple more examples to try. I'll just do this one really quick so you don't write it, but just so you can see the process. So same direction, find the inverse. What I would do, let's see, red was my word. So I'm going to switch the x and the y. So there's my x. There's my y. And then did I use green? Step 2 was in green, solve. So now, notice how everything is being protected by this cube root. So to solve, I have to cube both sides. So I get x cubed equals y plus 5 divided by 9. And the next step then is to get rid of the divide by 9 by timesing both sides by 9. We're just undoing the algebra. And now the very last step is to subtract 5. Usually we put 5 at the end. And we call it inverse. The other way that you could write it is knowing that instead of y, we can replace it with f of x. So those are the exact same things. Okay. Now the good news is you get some delta math practice tonight, so there's extra help videos if you needed a little more, but the steps are always the same. Follow those 3 steps. The hardest part is solving for y. Okay, so that's what we got. Inverse and composition of functions as the homework tonight. Remember, if you did not do the Chapter 5 test, that should be a priority that gets done tonight. And then make sure you submit your worked out solutions to Schoology. If you need any help, anybody on Zoom, you can come back at 1:35. And I'll be available on Zoom to help you guys out. Have a great day. Adios.